I'm Willa Anderson, and this is Polar Coordinates and Equations.
I'm sure most of us know what an XY graph looks like. But what about this? The first graph you just saw is commonly referred to as rectangular or Cartesian coordinate systems, created by this guy. He's also known for his signature line, "I think, therefore I am," but that's not important. The second graph looks kind of like looking down at the Earth from, say, the North Pole. And that's why it's been dubbed the polar coordinate system. Grégoire de Saint-Vincent and Bonaventura Cavalieri independently introduced the concepts in the mid-17th century, though the actual term polar coordinates has been attributed to Gregorio Fontana in the 18th century. In the Cartesian system, points appear on the grid in XY format. In the polar system, things are instead graphed in radius theta. We sort these values with ordered pairs. Funnily enough, theta is more similar to x and radius to y, because theta represents the argument, aka what you plug in, to a function. But we order it in radius theta to be different, I guess. Radius is the distance from the origin, a hypotenuse of xy coordinates, if you will. And theta, distance from our zero, which is always measured in degrees or radians. You can do sick stuff in polar graphs, like graph this, which looks like this in Cartesian, but also like this in polar. Funnily enough, sine of x and cosine of x are boring in polar coordinates. There are a few key kinds of polar shapes, which are like the equivalent of quadratic, exponential, and sinusoidal in Cartesian. These are lemniscates, limicons, carotids, spirals, aka Archimedes spirals, and roses.
For those of us looking for something beyond just totally awesome math, polar equations are for more than just looks.
First, polar equations model complex relationships that aren't easily represented in Cartesian. Calculating velocity of a ball spinning in a circle is simpler in polar, where there's a constant angular velocity rather than changing tangential velocities. So, is finding the distance of a circle the object has covered, simpler integrals. Polar coordinates are used often in navigation, as the destination or direction of travel can be given as an angle and distance from an object being considered. For instance, aircraft use a slightly modified version of the polar coordinates for navigation. Showing where a plane is simpler in polar. Basically, polar grids model our globe, and we use them in real life to represent spherical 3D space in 2D to make our lives easier, for calculations and representations. I hope you were able to learn something from this, or even just admire polar coordinates.